ad for people to see.
Ooh, how's that? Good?
You can see
Perfect.
it.
Oh, too far. There we go.
There we go.
You might be able to tell I'm not in Oregon at the moment. I'm actually in Tucson, Arizona. So I'm sitting here in a tank top in like 95-degree weather in the shade, and it's great.
It's actually really
Dang.
sunny and nice
Wait.
here though at the moment too. It's unusual.
Oh, good.
Yeah, I thought you were outside in Oregon, so you fooled me.
I thought it was Iowa.
No, also kind of looks like that, but definitely not quite. Could be anywhere.
How warm did you say it was?
It
How
was
warm?
95 when I checked earlier.
Wow. Yeah, that's
Which
the
is
main difference.
better.
It's a little chillier here.
It's been, my dad was telling me a stat that normally they have like 60-ish days over 100 degrees in Tucson. But this year they've had, I think we hit day like 107 or 108 yesterday, which is unbelievable that a third of the year has been over 100 degrees here.
Wow.
Dang, that is wild.
Yeah.
All right, I'm gonna give it I'll give it a minute.
Yeah, we started our schools one early, like probably earlier today, about 3 minutes late. So just FYI.
Yeah. Well, Riley, actually, if you want to get started, we're you know, about a minute in here. People will trickle in over the next few minutes, but yeah, you might as well just kind of start giving us some info. I'm kind of curious.
Cool. I'll get her done. Hello, everyone who's
right.
joining us. My name is Riley Loveland. I am a co-creator of Sustainable Building Week. My full-time job is working for New Buildings Institute. I also chair the Portland Green Schools Committee. I'm all over the place, but I'm really pleased to be here representing Sustainable Building Week today, wearing my little Sustainable Building Week hat. And I just wanted to say thank you all for joining. You know, this is our third annual Sustainable Building Week. We started this a couple of years ago, just really hoping to find some way to unify Portland around sustainability and collaboration. We'd had a lot of talks with people that just felt like we really needed something to help unify us. So here we are, third annual. This time it's virtual and 2 weeks long. On the screen, you see that we have 26. I actually think it's increased since 26. We'll call it just under 30 events this year. You can find them on our website, and most of them are being recorded. So if you missed a couple, go back and see if there's a recording posted. We want to say big thank you to our top sponsors here. Without you guys, we could not have done this in years past. And this year, especially, you really make it so that this is doable. And also a big shout out to our collaborating organizations. Thank you all. Again, without you guys and your brain power and your dedication to sustainability and, you know, putting these events together, Sustainable Building Week would not exist. So thank you so much. And really, that's all I have to say. I will be here in the background listening.
Great, thanks, Riley. Yeah, second year we've participated in Sustainable Building Week, so I'm really glad you guys are doing all this. So, all right, welcome everybody else. For those of you who aren't familiar, my name is Evan Schmidt. I am the outreach coordinator for TallWood Design Institute. If you don't know who the TallWood Design Institute is, I recommend you online and check out our amazing website. But a brief little intro. We research collaboration between two universities, including Oregon State and University of Oregon, hence our connection to Dr. Mark Fretz and Dr. Kevin von den Wymelenberg today. And we focus on timber construction education. So these meetups used to be in person, they've been virtual this year, and as part of outreach to help share information about what's going on in the world of mass timber research, mass timber construction. And these research brief meetups are brand new. So they're sort of a way to supplant our typical in-person research symposium with something that's online, a little bit more easily accessible, and kind of break up a little. Researchers have more time to talk about what they're doing. With that, I am going to hand off the microphone to our presenters. So we're being joined by, again, Dr. Mark Fretz, who's at University of Oregon, College of Design, School of Architecture and Environment. Mark is the Director of Knowledge Transfer for the Energy Studies and Building Lab, and I believe for Institute of Health and the Built Environment. Is that right, Mark?
Yep, that's correct.
And Kevin, Dr. Kevin van den Wymelenberg is the Director of the Institute for Health and the Built Environment and the Energy Studies and Buildings Lab, and is also a professor at the University of Oregon in the School of Architecture and Environment. So with that, I'll let you guys take it from here, and thanks for being here and looking forward to your presentation.
Yeah, well, thank you, Evan. I appreciate the invitation today. Can you hear me okay? My internet's cutting out. I might have to, I turned my video off, but let me know.
We can hear you fine as of now. I'll just interrupt if it gets really bad.
Okay. So yeah, thank you. I know there are a lot of familiar faces on the call, so this is great. We're starting to really build a good cohesive group here around these issues. And so I'll start just by kind of moving a slide forward and letting Kevin talk a little bit about the Institute, just who we are a little bit more.
All right. Hi, everybody. Nice to be here again. Thanks for all your support with the Institute and the TallWood Design Institute, rather. And hey, for that matter, the Institute for Health and the Built Environment, since I know there's a lot of crossovers. As Mark mentioned, the Institute is a kind of collection and agglomeration of a lot of different things. We love to partner with the TallWood Design Institute, though it's sort of no formal structural relationship between these groups, just a lot of crossover. Labs, if you will, collaborative labs, the Biology and the Built Environment Center, and I'll talk a little bit about that today. The Baker Lighting Lab, the Energy Studies and Buildings Lab, and soon we'll have another lab joining us with the Acoustics Lab. So far, we're going with the name Oregon Acoustics Research Laboratory. And there's also the NetZ Lab, Sports Product Design, a bunch of other university partnerships on matters related to health in fields from physiology to medicine, engineering, psychology. And then maybe some of you are aware of the Institute's industry consortium called Build Health, which is bringing academics together with industry to solve real world problems, hopefully on a time scale and in a manner that it's appropriate and applicable to the problem at hand. We believe industry helps us ask better questions, helps us think more creatively about solution sets that also hopefully won't be sitting on a dusty shelf. Instead, will find their way into practice. So that's the idea. Mark, I think you're going to start, and then we'll do a little back and forth. And
Sounds great.
I got to bail at about 4:30. So.
Sounds great. And I just wanted to quickly point out that some of the work you'll see here at the beginning seems a little bit, different than what you traditionally see in these meetups. And that really is the result of these unusual connections, these innovative kind of cross or transdisciplinary connections that we've got within the Institute. So with that, we will start talking about a little bit of biology and mass timber, and specifically the mass timber microbiome. To set some context to what Kevin will present, I kind of want to talk about a project that we had, we still have going on. It's not completely wrapped up, but it's working together with Portland State, looking at how molecules and microbes play together with different building materials. And so in this particular project, we looked at 4 building materials, earth and plaster, painted drywall, mass timber, so CLT, and concrete, and put them out in the office environment to let them get microbes from all of us in indoor conditions for a while. And then after they were in the office environment, put them into these microcosms, which you see in the image to the right here, and sampled on a regular basis the microbiome on the surface, as well as the air and the VOC content in the air, and paired those two data streams together to understand what was going on a little bit better. We were inspired, or at least I was inspired, by cheese making and how in Europe, this has been done with wood intentionally for centuries to be able to establish bacterial communities that would help the cheese ripen within the wood itself. So this was something we thought could be really interesting with mass timber buildings. In the preliminary findings of this study, you can see these graphs, this graph with the dashed line, well, the solid lines indicate just microbial abundance, actually bacterial abundance on the surface of the different materials. They all start out about the same. You would imagine earth and plaster, dirt has a bit more, which it does. But the interesting thing here is the dashed lines, which show the actual viability of the microbes. And you can imagine, again, that dirt has got a lot of, microbes that are very alive. But in the timber sample, you see this dip quite a bit more than the other microbes. And so we thought that was quite interesting, and kind of dug in that a little bit more and looked at the VOCs coming off of the different materials. And of course, with mass timber, you have a pretty strong signature of terpenes that the other materials don't have, and some other aspects about the material, such as surface topology of the mass timber structure that's a little different. So that said, we started looking at some additional literature and found that other researchers found similar things about bacteria on wood surfaces, that wood surfaces transferred bacteria less easily than smooth surfaces such as plastic or stainless steel, and actually had lower counts of viable microbes on unfinished wood, even lower counts than on plastic, and couldn't even be detected 48 hours later for Staph aureus on untreated beech wood. So wood was exhibiting some natural antimicrobial properties, and even within a year ago on this paper from 2019, starting to talk about wood as being a hygienic material, which is somewhat counter to maybe the common narrative. So there was a famous study in 1984 by Roger Ulrich looking at wood looking at biophilia in view and how that improved outcomes in healthcare settings. And we all are aware of the biophilic aspects of wood and its patterns. And so we started thinking about this and how this might, right now translate into healthcare settings. And healthcare typically translates it into more tones of wood tones and plastic laminates in wood. And one of the big barriers, we believe, for not having real wood is the infection control issue, which is what these papers are starting to get at. So instead of using real wood in healthcare spaces, you see a lot of synthetic wood products. So there is a concern about infection control, and that is really kind of the work we're doing now, is to understand how might this product be used in healthcare spaces, or other spaces for that matter, understanding how the microbial aspect performs. So I'll let Kevin start talking about that.
Yeah, well, I think this question and the potential of these health benefits associated with wood, and those are many, potentially from antimicrobial compounds, sort of natural inactivation, perhaps even flourishing a healthy microbial community to provide some natural defense mechanisms, as opposed to our current approaches to kind of hygiene, assuming that's the current assumption of hygiene is kill all the bad stuff. Maybe there's a concept around foster resilient communities that disallow the growth of nasty microbes. And then other concepts, Mark mentioned some of the aesthetic concepts that have shown to have, true physiological benefits, not just aesthetic benefits. Turns out you start digging deeper, scratch beneath the surface a little, and there's a reason we like corner offices with wonderful views, and there's a reason we like natural materials. And those reasons I would argue historically been undervalued and sort of simplified. and written off as an aesthetic, luxury, as opposed to some sort of legitimate physiological value add or microbial value add. So I'm hoping that the two projects I'm going to really quickly describe will help to further an evidence-based approach to understanding the health benefits associated with wood that I believe are possibly there. So this is, I'm going to show it as one project, but there's actually some components here of two projects. So the one I'm highlighting is supported by the TallWood Design Institute through the Agricultural Research Station grant, and it's in partnership with Gerald Presley at OSU. The kind of these two grants piggyback off one another. They were both funded within a couple of months of one another. The other one is a wood innovation grant supported through the Forest Service. So some of these things apply to both. So next slide, Mark. A lot of this is just reiterating what we've just been talking about, kind of these unseen, hidden benefits of wood. Wood is porous, which supports two ideas I wanted to talk about. One we've discussed, which is the potential inactivation of pathogens through selective antimicrobial qualities associated with wood, including, I believe, the porosity, and therefore starvation of oxygen, by using that capillary action to bring biomass into the pores and starving it of oxygen, and therefore inactivating it. Or perhaps just bringing it in through that capillary action and not allowing surface exchange when you contact those surfaces. And then potentially supporting beneficial microbial structures with community structures with the surface of the wood, and actually some of the kind of hygrothermal characteristics of the wood, which leads me to the second point, which is humidity buffering. And we're learning a lot more about the value of mid-range humidity in indoor environments. In fact, we wrote a lot about that at the beginning of the pandemic in March, about the inactivation of viral particles. But more even, I would say more important than the inactivation of viral particles, which it does show that in particular, like influenza has a more rapid inactivation at 40 to 60% relative humidity. And other coronaviruses show some similar relationships, and not as much data is available for the SARS-CoV-2, but the data that is available seems to follow the same trajectory, more rapid inactivation. But I would say maybe more importantly than that are just the fundamental particle physics associated with spaces that have more mid-range humidity levels, which is particles drop out of the air more quickly than they do in very, very dry environments. And in many of our northern latitudes, especially during the winter, when outdoor air temperatures are low and we are heating the air, we're zapping all of the moisture out of the air, and we're effectively living in deserts. And so particulate matter can remain aerosolized much, much longer, which I think is perhaps partly why we see increased infection transmission during the winter season. And then the other piece about that dry air is it actually has a human physiological impact, which is it dries out our mucous membranes. So if we can think about natural materials like wood or clay and bricks that have these natural humidity buffering profiles, we can avoid some of the negative concerns about overhumidified spaces and mold growth, but also the less understood, but perhaps equally concerning negative ramifications of very, very dry indoor air. And then, of course, from a research perspective, we want to prove those things out with evidence-based approaches. So we'll be using our DNA and RNA molecular-based assays to understand the microbial community structure, persistence, viability, et cetera. And then also from a very applied standpoint, we have to understand the impact of coatings. So we'll be looking at all of these with bare and exposed wood, as well as multiple coatings. Next slide.
Yeah, I just wanted to mention also a couple of different types of coatings. One that's more traditional and one that's more bio-based.
Yep. And I think this is one of the three studies, though I can't remember which one, Mark, that you had previously shown. And it's just shown, and it's just, if you look at the bottom line, you'll see the uncoated and exposed wood appears to have the more rapid inactivation of a range of different biological agents. And it's all too small to read, so sorry about that. But we can share those papers certainly if you're interested. And then the next slide just starts to show the study design a little bit. And actually some progress. These are both relatively recently funded. I think start dates maybe were September 1st or October 1st. We actually got a little bit of a jump start on these because of the lead times of acquiring some of the materials we wanted to get moving. So one of the partners on this project was with Wymelenberg. You're seeing this sort of the 3 lam pieces of CLT cut there into circles, which are then diagrammed in the bottom image associated with our grant with Gerald Presley, supported through TDI, and then a similar approach, but just using blocks, chunks of wood for the Wood Innovations grant. Similar sampling configuration in that one. And then the next slide kind of illuminates these ideas a little better. So again, Wood Innovations on the top, ARS on the bottom. We get to use some fun toys for these projects. On the top, you see our microcosm chambers, which are poor man's glove boxes that we assembled in, I don't remember how many of these we have, something like 15. Lots of controls, and then all of our samples in triplicate. I think we've got negative and positive controls, 3 of each, and then our samples in triplicate, multiple material types. For the Wood Innovation Grant, actually, we're looking at just a spruce pine fir 3 lam coated with a Sanson KP12 product, as well as an uncoated product. And then we need multiple versions of this because we have several different wetting events. So to really drive at that concern around potential moisture in buildings, and think of these wetting events as trying to simulate leaks of different intensities, or perhaps even a soak or a long-term leak, either as you can imagine from a job site, construction process, or maybe a long-term leak or a flood that might completely saturate certain pieces of the wood. So those are the kinds of scenarios that we're looking at. And then using a DNA-based molecular approach to understand the bacterial community structure, using what's called a 16S assay. And then the ARS grant, the TallWood supported grant on the bottom with the rounds, you'll see we're actually going to be able to use our climate chamber to modulate temperature and relative humidity, so we can look at indoor humidity profiles that are different. In particular, kind of a traditional and an ideal. So a low, like a 20% relative humidity, and then an ideal managing something in that 40 to 60% range. And then in addition to the Sanson product for the bottom set of graphics and the unsealed product, we're also trying a Osmo bio-based kind of a plant-based sealer. They call it a food grade sealer. All of these with the idea kind of remaining aesthetics. The aesthetics are important, so we don't want to do anything that's really discoloring the wood. We're looking for a clear matte finish in all of these. And in the bottom, we're using a spruce pine fir as well, but then also a Doug fir larch to get at both sides of the Cascades as a source. So with that, I'll give it back to Mark.
Yeah, I wanted to mention one other thing is you see that box with light coming out. We're for the ARS project, we're going to have these in kind of metal chambers with a window essentially on the top, so that they'll be exposed to office lighting conditions as well. So we're using light since we've studied light in other microbiome studies and know that it has an effect on the microbiome. For the healthcare one, we're also going to use a cocktail of bacteria that are found commonly in healthcare environments to start off with these. So switching now to mass timber acoustics. So why acoustics? Well, and I know this is an abrupt shift from the microbiome, so I apologize.
Whiplash.
We have really kind of 3-hour-long presentations in one here. Well, acoustics are important, not just because there are a lot of code regulations and jurisdictional requirements, but we also know that, you know, more and more acoustics in buildings have an effect on health. There are guidelines that have come out from the World Health Organization in Europe outlining a number of health effects due to acoustics. As cities get denser and people live closer together, acoustics are more and more important to keep us all happy and keep you know, tenants happy and rents stable, so that people want to stay where they are. So this is becoming more and more important. It turns out also that a lot of times, you know, with improved acoustic performance, you get improved energy efficiency just by better wall assemblies and you know, windows and such. So this is something that we've been interested in due to the health and energy aspects. And of course, mass timber we're all interested in, but mass timber, you know, wood is a great material for music instruments because it's resonant. So that makes it challenging, but to do in these types of situations. So we undertook a couple of different studies to really start to understand how can we get the best of both worlds. How can we get the mass timber visual aesthetics and the acoustic performance? So this is maybe not the right sequence because Kevin only has enough time. I want to have him talk about the way we can test this and what we're trying to do at University of Oregon.
Yeah, so it seems like the theme for tonight is going to be, I'm going to talk about what we're about to do, and Mark's going to talk about what we've actually done, which is actually kind of fitting because I spend more of my time trying to figure out what we're about to do. Anyway, one of the big things we're about to do is build a world-class floor-ceiling acoustics test laboratory, and I couldn't be more excited. This will be the biggest project I've ever had the chance to sort of conceive and maybe use that analogy, birth, and hopefully, you know, build and become grow into the world and make something of real impact. So I'm really excited. The goal here, as we started to explore the sort of challenges facing architectural acoustics with regards to mass timber, the obvious multifamily housing opportunity as a really great target market for mass timber products was there. And the obvious problem with that, among a few others, but one of the major ones is the noise trespass, especially at higher end housing markets. Now, I'm a big believer in sort of equality and in spatial justice, and so I want to find ways to create low cost, high performance acoustic assemblies so that all income brackets can afford to have a wonderful mass timber building that also has good performance from an acoustics perspective, and we don't have to have the stress. Again, the physiological impact of this is there's stress associated with background noise and neighboring noise or neighbors noise. And you probably all have an experience in your life of hitting the ceiling with the broom or stomping on the floor. And we want to make sure that we can provide solutions that are going to solve these problems. And so I thought this wouldn't be as hard as it turned out to be. It's a really expensive process to do acoustics testing, floor ceiling testing. There are not very many labs in the world that do it. All of the labs in the world have substantial problems, and very few of the labs can accommodate some of the assembly depths that we want to explore, or the weight of some of the assemblies that we want to explore with mass timber. For example, one of the projects Mark's going to show it took us several months to get the results because we had to build the assembly inside of the chamber, inside of this giant floor ceiling box like you're sort of seeing on the screen. This is our design with a local firm, and the project that took us 3 months to do, where we had to build and wait for the concrete to cure before we could then run the tests, we can theoretically do in a facility like this within a day, and it took us weeks and months to do it, to iterate through the variables that we wanted to explore for the results Mark's going to show. So these are the sort of construction or design development level drawings that we worked on with TDA. You can see just barely in the small lower left corner there, the logo. This was built upon some previous work that we had done with SRG. And all of which was done with some acoustic consultants from Seattle, Jerry Lilly, TVA, or Jerry Lilly, sorry, is JGL, and a gentleman by the name of Matt Golden, who works for a company that manufactures acoustic underlayments and things like that, but also he's one of the most advanced lab users in the world, and so we wanted to get his input on the project. This will all live within a large warehouse building. I don't know how large we'll be able to afford, but that's one of the big questions. And you can kind of just get a sense here that it's designed for high throughput, because we've got the ability to build assemblies on two sides concurrently and slide them in and out of the chamber. And then there's multiple laydown areas so that you could actually have multiple assemblies being constructed concurrently. When we wrote the proposal for the funding for this project, there were no facilities that could do mass timber testing of any quality west of the Mississippi. Really, there were none. Now there is one other facility, but I've got it on good word from a trusted expert that it's not a very high performance facility. And so if you're going to have high quality assemblies, you really can't test it there. And that's really unfortunate, of course, for them, because they made a big investment. But we've learned from their mistakes, and I believe we'll deliver a really high quality product. The next couple of slides just show a little more visuals of the concept of how it might fit inside of a building, and some of the activities. And of course, we branded the final one with TallWood there. It won't be a wooden box. It might have some wood on the outside of it, but they're large concrete boxes, very massive in nature. So with that, unfortunately, I talked a minute past when I was supposed to run. Mark's well equipped to try to answer questions, and if he doesn't know all the details and you're still looking for more, I'm happy to chat.
Perfect.
Another day. Thank you.
Yeah, thanks, Kevin. So why don't I continue? I'm going to show the lab testing that we did and some field testing, and then I can answer questions at that point. And then I have one other smaller project smaller presentation on a larger project that we just started that I want to share at the end. So I definitely want to leave some time for questions. So as Kevin mentioned, we did this lab testing about a couple of years ago now. And as we started looking around the industry, there were specific challenges to mass timber that, that became very quickly apparent. And you can see on this image on the left here, one of them is just the size of doors that facilities had to get product in. Very few had a way to get a large panel into a chamber or even into their warehouse. And that's one of the things that, typically they do a lot of stick frame testing. So that's one of the things that was challenging, was to find a way to do that. And then of course we had to have a joint in the panel, which was less than ideal. Or you can see in the far right image, just not having the equipment to be able to handle that massive of material. And so a lot of manpower. To begin this one, we wanted to understand what we should even test and why. So we started by developing a survey, going through the existing literature, everything we could find, a lot of what was published by Woodworks and what was published at the time by different acoustic product manufacturers, and gathered that information, gathered as much Canadian information as we could find as well. But it was important to us that we developed assemblies that industry really wanted, that that we were actually hitting the right target, and that we were testing them to ASTM so that they could be adopted by jurisdictions here in the US. So we started with, and we got that survey in the hands of probably a lot of you on this call, but contractors, architects, engineers, acousticians, some developers. And what we heard back was primarily we want to use generic materials. We don't want to be bound by proprietary assemblies, especially as we go through VE. We'd like to have third-party testing, even if there's testing already out there, because just to make sure that these assemblies are verified by a third party is important to us. Use as little wood fiber as possible. Ideally, develop 3-lam assemblies. They should be quick to assemble. The mass timber should be visible and not encapsulated. And that we should also get some data on the structural composite, which we saw last week on this call for the high seismic areas. So we got that survey back, and from that we developed a few assemblies in CLT, and I don't have drawings here, but we also tested these. At the end, we added MPP as well with the same assemblies, which you'll see in the results. But we have the structural composite, and then we have that same thing where we have a wood floating floor topping, and then another one where we add an acoustic mat and a build-up in the floor. And then we heard a lot that most of the people we surveyed wanted to try to eliminate wet trades, and what might that look like, and how how would an assembly look. So we did do an assembly that used cement board that was built up with acoustic mat underneath it, with a couple of different toppings on that to test as well. So those were the assemblies. For the wall assembly, we just tested first, bare CLT, and then added drywall, and then added a rain screen, thinking about how this might be used in that configuration. So here are some of the images, and actually I wasn't on site, but Evan was on site together with Dale Northcutt from our lab, and so they provided some great images for us to get a sense of how this went down. So I'm sure Evan could also help answer questions if we have some about the actual process on site. But you can see, we've got 2 chambers. There's just, a big hole between the 2 with heavy walls, double walls there for sound isolation. And then, like I said, because the doors were so small, we had to bring these in 2 panels, and we did a lap joint. And then you can see the process of just building this assembly up in the chamber. They use some putty to pack the edges with sand for density, to seal around the edges. And then they have a sound transmitting chamber on top and a receiving chamber on the bottom with instrumentation. And so that's for the STC tests. For the impact class tests, there's a calibrated weight testing machine, I guess you can call it, that drops these calibrated weights onto the sample, and then the sounds are recorded below. Here you can see the dry assemblies being built up. We did them, the final we did with and without carpet. Carpet is pretty amazing, and how well all of a sudden that can perform. And you can see the concrete composite being built up. This is what Kevin was talking about, and that we had to find a lab that was willing to let us basically take their lab out of commission for a month as the concrete cured. So if you build this in the chamber itself, that's one of the problems. So the lab that we're developing will allow these cassettes to be made to the side and then slid in and out so that you can have higher throughput. So you can see here's the MPP, and the results are on this slide. You can see the MPP and the CLT were not exactly the same thickness, and this likely affected the performance between the 2. The CLT was 6 7/8 inch 5-lam, and then the MPP was thinner. It was 6 1/8. So there are some differences there. So the IBC code requirement for housing is 50 for STC and IIC. You can see that dashed line there to understand in the lab test how would these perform, and would they meet housing requirements. And you can see the structural composite with the acoustic mat and the floating floor would meet that and actually performed really high. Same for the dry assembly, and adding carpet. Of course, it performs really high in the impact category. Strangely enough, you can see it as soon as with the concrete, the topping in the structural composite, it actually, the impact performed worse than just bare MPP and CLT. And so, by the way, there's a report on TallWood's website that has this information if you're looking for it. So in the wall assemblies, you can see, this was actually done by USG, and the other one was done by Riverbank in Illinois. The wall assemblies just being vertical, and we had weather barrier or rain screen configuration here, and the wall assembly results are as follows. And one of the performance indicators here is OITC, and that's an outdoor-indoor transmission class that applies to exterior walls. And so that is, not usually, there's not usually a code requirement, but the higher performance would give you a better sound isolation. And so that's something we wanted to look at as well, given the slides I showed about better performance in higher density cities and health benefits. So of course, those are lab tests, best conditions, although we had to place a joint in the panels due to the size. It's, of course, never the same as actually going out into the field and having penetrations between floors and, different conditions at the panel edge. So we wanted to test some assemblies in the field and compare how these performed to our lab tests. That is more challenging than it seems. I mean, one of the most challenging things about it is just finding research settings first that you can get into where the tenants are okay with you getting into the space on both floors. Sometimes you'll get a tenant that's okay with it in one space and the tenant on the other floor was not okay with it. We went to several buildings where just the size of the spaces were wrong and didn't meet ASTM. We found building owners that didn't, they actually wanted to know, but they didn't want us to do the test because they didn't want that information out there. So typically we had to promise that we wouldn't identify the building. So the buildings we tested were 3 different ones in the Pacific Northwest. And the assemblies that we tested were a CLT concrete composite assembly, structural composite assembly. We tested a heavy timber assembly with a concrete topping and an NLT assembly with a concrete topping. So those are the 3 different ones. You can see, what this involves, and a lot of times it's getting in there when a space is finished, has, construction complete, but tenants haven't moved in, or, it's weekends or early morning. We got kicked out of one space because it's really loud and people were working on a Saturday, and so we had to come back another day. So those are the challenges with testing in the field. But what we found with the tests in the field was that that they performed pretty well. In fact, the IBC field test requirement has got a derated factor for that performance versus a lab performance. So to meet housing requirements, you got to hit 45 in the field versus the 50 in the lab. And you can see from the graph here that the NLT and the CLT composite both would have met that requirement. And the heavy timber is very close. Yeah, given all the complications of flanking and penetrations and things like that in the field, they still performed really well. So that was good to see, and it was good to compare between the lab tests. So I just want to acknowledge, this was a large team effort, and funding provided by TallWood and ARS. And then the facilities, like I mentioned, for the lab tests were Riverbank, Acoustic Laboratories, and USG, and a lot of industry feedback to be able to help us really hone what we wanted to do. So I'm going to pivot a little bit and just to talk about, these tests. It's pretty expensive to do these tests. You can imagine, the cost to create the assemblies, to travel costs, to to get all that set up is not inexpensive. So you want to make sure that you know what you want to test and why. And so for designers, we want to be able to iterate on designs and come up with new concepts faster. So what we are doing now is we're developing, and this is actually not what we're developing, but an example from a test, little test box that we had in a class to demonstrate to students some different assemblies. We want to design a better small acoustic chamber that we can actually test some small assemblies on in a more iterative, rapid fashion. It won't be any kind of ASTM test, and it won't be, we'll miss low frequencies, but we think that we can get some better feedback for design iterations. We want to test recycled materials. We want to test some different, we want to look at the carbon in the assemblies and see how we can get to lower carbon assemblies. So this is something that was funded this year by TallWood and ARS, and we'll be launching into this very soon, and then have this available in our Portland lab to be able to do this work, and also to work with firms around the area to help iterate on designs before we scale up and really do full scale testing in an ASTM certified lab. So any questions on that? Maybe I'll take some questions on the acoustics or the microbiome, and I just want to share the next segment. And if not, we can also, you can save them, and I'll do the next one, and we can come back.
Well, Mark, we have one from Scott Noble that kind of speaks a little bit to some of what you just talked about, because he's wondering how you compare the value of basically lab testing versus field data. So the question is, acoustic information is scarce for constructed mass timber buildings. What is the value of data from real world projects versus laboratory testing? I guess that's it.
Yeah, so the IBC actually lets you use field testing to get to a performance threshold, but they have a D-rate factor because they know that field testing is never going to perform as good as an idealized lab test. So it's, for the housing, it's 5 dB difference. And so there's still value in doing that. And sometimes there's also the value in learning from how something actually performs in the field with all the conditions such as flanking that you don't get out of a lab test.
Great, thanks, Mark. I may have accidentally stopped your video as well. I don't know if you turned your own video off.
I see that. Okay, so is it back again now?
Yeah, your screen is showing. Yeah,
okay.
Good.
Any other questions on that? I can come back to that too if you think of some. If not, then I want to talk a little bit about our last project that we've launched. I guess it was about 3 weeks now ago that we started it officially, but it's been cooking for a lot longer, and we've been working on these issues for a lot longer. And I know they're all important to everybody here on the call. The project is called Carbon Narratives for Design Planning, and this grew out of several of us. So Allison Kwok, co-PI, myself, Kevin is co-PI, and Judah Shine have been working with students doing whole building life cycle assessments over the past few years, and also with industry partners out there. So with actually working on real projects, doing assessments, and starting to understand what the issues are when we look at carbon in these projects, and how that story is sometimes confusing for designers and hard to understand when we want to make decisions. So designers, have a big role to play in carbon in our built environment, from the design and construction side, the operation of our buildings. The materials we select, though, are huge, and there's so many material issues that we need to consider, such as where is aggregate coming from, how is it being mined for concrete, the emissions in cement production, wood, forestry, all of that, the pathways for end of life. So we know that we have a big role to play in the climate change, story. And a lot of that is thinking about the embodied carbon in the materials that we choose. So there are a lot of tools being developed to help designers do that. A couple of the more popular ones are Tally and Athena. And these tools are great, but when we start to use them and look at the results that come out of the mass timber assemblies, sometimes there can be some really wide disparities for the biogenic carbon piece. And you can see on that chart on the left, just an example of the difference between Athena and Tally is tremendous. So the assumptions that are made, how much gets landfilled at the end of a project, how much gets incinerated, how much gets recycled, how much carbon is actually stored in the panel versus not. All of those are assumptions, and they hugely impact the carbon story. And so we as designers want to be able to understand really what the story is more clearly, to be able to select materials and be able, because there's so many variables in a project, that we want to be able to understand this piece of it more readily. So the goal of this project is really to bring together designers and scientists, industry and government to think about where are the gaps that are causing this disparity in the carbon story. What are the issues? What are the assumptions, and where are we getting that data for the assumptions? What do we know? What do we think we know? What do we not know? And try to get a common narrative so that we can all understand together what that story is. So this is going to result in a group of experts coming together for an initial workshop in April, right after the Mass Timber Conference, and then a follow-up series of work sessions. And we're targeting, right now we're developing a survey that's going to go out to the AEC community and manufacturers, that we can start gathering kind of current state of knowledge. And we're doing a large literature review building on work that COPI Allison Kwok has already done. And we're going to get that all together and then actually look at not just North American forestry, but European forestry practices too, since we know a lot of panels are coming from abroad, and so it's not just the U.S. products that we need to focus on. So that's the goal, and then the output is, we're going to think, like I said, big and globally, so that we consider the supply chains that everyone's using, and the goal is to really develop education, a handbook, hopefully, that would be useful for designers in the studio, or some form of a guide for designers, so that this information is clear, and we understand what the carbon content of wood is without such a wide margin of uncertainty, is really the goal for this project. So I know that's a large goal. It's a huge project in that sense. It takes a team though, and a really big team, and we're very excited to have a lot of industry partner support to help with this, and of course the support of Quorum. They have expertise in forestry, and TallWood support as well. So that's the project that we are working on right now, in addition to these others. And I'd like to hear any questions about all of these now. I wanted to leave time for some Q&A.
Great, thank you, Mark. Yeah, let's just open it up to Q&A. There isn't anything in the chat box, so if you have a question, please just go ahead and voice it directly.
I want to give I see that Simone O'Halloran's on here. She was actually one of the students that did a whole building life cycle assessment together with Hacker. That was a great example of understanding the kind of the disparities in the tools in the wood category. So that's one, but a lot of other student work that's really kind of led to this really good stuff. Questions? With the time we have, I'm curious to hear from all of you. Like I said, we're developing a survey, but what would be some things that you all in your work would find important for us to understand? I know the Carbon Leadership Forum has done a lot of work on this. They had a series of webinars. We want to build on that and not really repeat that. So I'm curious to understand what everybody here would find important for us to really dig into a little bit more. I might have to start calling on people, looks like. Don't be shy.
I think you should do that, Mark.
All right, William, you're first now.
William, you're it. I know.
Okay. No, I think it's really great. It's comprehensive. A little bit of whiplash on three like really critical facets of what we're experiencing with mass timber. I think, you know, the carbon discussion is something that, because the tools don't align, as you pointed out, I think is really, you know, creates a lot of challenging discussions. So I think, you know, driving a better understanding, driving better tools and assessment, I think is really the goal of what you're hoping to achieve over the next couple of, I think it's a couple of years, right? Is what you indicated.
It is a couple of years. The workshops will start after the Mass Timber Conference, April 2nd, that Friday. And then they'll be spaced, the work sessions will be spaced apart. And then the final output will be in year 2, you know, so the kind of the guide. So we definitely want to hear from, you know, architects, engineers, contractors. You know, we want to hear from a wide range of others, you know, as well. So, this together right now and getting the questions that we want to drill into more.
I think what might be good is for people to have availability of the information, and then maybe have almost like a scoping, brainstorming discussion about some of the things that we find as disconnects in the messaging or the information around it, just to kind of like take that into consideration in the development, because I think it'll really be a pivotal piece that will refute some of the false information that's out there. And so hopefully there would be an opportunity to do that. So I guess a little bit less of a question, but more of an observation from how those conversations have gone. And we were very excited not only about the, you know, now to jump, we're also very excited about the acoustic tools that you've already developed, because that's really helped people to start to have a discussion, but are looking forward to the research laboratory contemplated. So pivotal messages. Now call on somebody else. No, okay.
What about, anybody have questions about the acoustics or the microbial work that's going on at U of O? I know that I reached out to a handful of people looking at different, you know, different sealants that we wanted to use. And so this group has been really important to us to make sure that the work we're doing is actually relevant, and you know, it's something that industry would use, and not, like Kevin said, something that we put in dusty journals. So this is an important sounding board for us to make sure that we're providing a pathway to practice.
So
what is the, Mark, I'm curious, what is the maximum size and sort of scale of the panels you can test in the acoustic facility when you get that up and running, in terms of depth and then just the panel width and length?
I believe the opening, and this is where Kevin needs to be on the call because he's been involved in the design of the actual chamber, but I believe the panel opening is going to be 10 feet by 12 feet. And that will be, that you could do a single panel, where we had in the other facilities we found, it was difficult to get that panel in. So that's going to be, and I'm not sure the depth. I want to say probably it's at least 1.5 feet, if not more. So.
And then I have a very important scientific question. So can you just use like Van Halen running with the devil as the sound that you're trying to, you know, block through the floor? Or do you have to use pink noise, white noise, or?
Well, I'm not sure, first of all, that you'd want to block that. I mean, I would be okay with listening to my neighbor's Van Halen, but yeah, it's a white noise and pink noise. There's a whole range of frequencies in there. It's kind of a cocktail of frequencies. So, and it is pretty loud. And we do that. We have this kind of stand that we set up with a speaker, and so yeah, it is a prescribed set of frequencies.
Question on the microbial research. So you talked about pathogenic microbes, but then there's also healthy microbes. I'm wondering, what are your thoughts on that? Like, is wood selective, and are you just kind of killing all microbes? Like we don't really want to be using antibacterial soaps, and there's the whole microbiome and that sort of thing. So, do you have any thoughts on that?
I do. In fact, and that's exactly right. We don't want to just sterilize and kill everything, because we know more and more that that there are a lot of beneficial microbes, that we are composed of microbes as humans, and we need microbes to keep us healthy. And there's also a lot of times microbes are commensal. They do things like help us digest food and help protect our skin from infection. So we need a lot of microbes. The good ones a lot of times will outcompete the bad ones. And so if you sterilize spaces, a lot of times you get an overgrowth of the pathogens, the bad ones, or at least you provide a niche for them where they can use the resources to overgrow. It's interesting, if you notice this graph, can you see my screen again? Everybody? I just pulled that
Yes.
back.
Yeah, we can see it.
If you notice that in the wood, there was a bounce back after day 8, the viability started going up again. And so we're actually still trying to get more data there to understand what was happening. What we think was that maybe a different community that was better suited for wood was starting to develop on there, right? And that doesn't mean it's bad. It's probably a community that you would typically find on plants and leaves outdoors that humans have evolved with for ages. And so it just shows that some of the microbes that were in the office, probably those that are human associated coming off our skin and from our guts and respiratory systems, were starting to die off. And that, like Kevin mentioned, a few different pathways. One is the porosity. They just kind of get swallowed into the pores. Another might be desiccation, where the wood just dries them out. And then the third might be the VOC component might actually, the terpenes might actually inactivate them, which makes sense, right? Trees can be in wet environments and not get attacked by microbes because they have protective forces. So we don't want to kill all the microbes. We want to basically just curate the good ones, the ones that humans have evolved with and are commensal, that aren't bad for us but support our health, and basically outcompete the resources for pathogens. Is that what you were asking, Rachel? Sorry.
Yeah, I think so.
Yeah.
I can follow up with another question on the carbon narratives. So is your research, is it more intended to look at comparing the different tools, or trying to dig into like really what is the carbon story for wood, and maybe even like, I'm wondering, would you go as far to look and try to evaluate ecosystem services and bring that into the dialogue around why we use wood?
Yeah, it's not so much focused on the tools themselves. It's more on the data that's feeding into the tools that's causing kind of the assumptions to be wide ranging, and where do those assumptions come from? What's the data that's used to kind of feed those? And hopefully the tools we can work with folks to maybe start to change that so the tools become more consistent. But it's really more about the data. As far as ecosystem services, I'm not sure we've fully explored that yet, but I think that's something that would be really a great outcome.
Just a comment on the Douglas fir, which is a moderately durable wood. So that might be accounting for some of your microbial changes, because it does have chemicals that will affect microorganisms fairly well.
Yeah, the CLT that we tested was Doug fir for our preliminary study.
It'd be interesting to see what happens if you put a pine on there or something that has less and other things.
Yeah, and then the other thing is that in this actually test, the biologists who are not architects coated it with linseed oil, and so it is
quite attractive to fungal.
I'm sorry?
Linseed oil is quite attractive to fungi, to food
Yeah,
sources.
we actually had a mycologist was the one that coated that too. So So, but we want to do it this time. We're going to do it without any coatings, and then of course with some different coatings.
Mm.
And,
Cool.
yep. And then Elliot Gall's lab at Portland State is the lab that's going to work with us again. He and his assistant are going to do the VOC testing. Yeah, great questions.
Maybe time for one more question. I don't want to hold people up too long, especially you, Mark. So maybe one more question. Anybody have something pressing? Can't live without asking.
Hey, Mark, that was a very nice presentation. It seems like one of the difficulties with the carbon question is this end of life, and it looked like you had quite a bit of disparity between the different models at end of life. Do you have any deep thinking about how you predict and how you give someone a good tool to talk about what's going to happen 50 or 60 years out? Do you have to assume there's a certain amount of design for disassembly and things like that?
Yeah, I mean, that's a great point. One of the things we've considered is, is really kind of digging into how the designs themselves might change and looking at that from a design perspective and what's currently being done for disassembly versus how could the panels be designed for more disassembly. So we're, like I said, we're at the beginning of this project and haven't dug into it too much, but we want to understand kind of current state. And first of all, are the assumptions in the tools correct for how the material is actually being used? And then another part of it might be what might be to improve the end of life story.
Mark, you're kind of cutting out here.
But this is squarely, that's squarely in our wheelhouse, though, to be able to, think about the design aspects for end of life. I think it's a great studio project for some students, or a charrette in any case.
Great. All right. Well, if you have more questions for Mark, I'm sure, I don't want to speak for you, but I'm sure you'd be happy to answer them by email or something. But Mark, thank you so much for coming and presenting here. Really appreciate it. Say thank you to Kevin as well. We'll give you the silent Zoom round of applause here.
I appreciate it.
Yeah.
I'm going to put my, I'll put my email in the chat here in case anybody has any pressing questions. You can email me.
Great. Yeah, so to everybody else in the meeting here who is left, we are going to be joined by a couple different folks next week. We'll be talking about one project which looked at Oregon's mass timber supply chain. So this was sort of an in-depth study of the supply chain specific to Oregon and sort of more broadly, I guess, the Pacific Northwest. And that'll be led by Alex Zelaya, who was formerly at Hacker Architects. And he left Hacker about a year and a half ago. He's just completing his MBA at University of British Columbia, I believe. So he led this study in conjunction with William Silva at Swinnerton Builders, who I think might still be here, and our own director, Ian McDonald. So join us next week to hear from them on this supply chain study. And we'll be hearing from one of the faculty here at OSU, Lech Mazinski, about a project that did a global survey of CLT manufacturing. So kind of a look at different practices, both at the technology front as well as the business front. So if you're interested in supply chain, join us next week to hear about those projects. And yeah, we'll take it from there. So thanks, everybody.
Thanks,
Mark,
Evan.
Mark, thanks, Evan.
Yeah.
Thanks, Evan.
Yeah.
Thank you.